This is the 36th exercise of the list that I gave you, and I think that this is interesting because we start with the logic diagram. You know, some gates that are not the most usual are used in this circuit, so it's interesting. I think that this is the most difficult one of this kind in the list of exercises. So we are going to solve the first DF, the first logic circuit, because according to the exercise we have to find the Boolean expression for the F and for the G. Since the F is the most difficult one, I'm going to calculate the Boolean expression of that F according to the 4 inputs and the circuit. You see that we have 3 levels here. So I'm going level by level, having the expression. This is the XOR gate, if you remember, and this is the same but with a little circle. So it's the XNOR, the negation of the XOR gate because of this small circle. So here we have the XOR of Y and T, and here we have the XOR of C and X, and here at this point we are going to have the XNOR of both expressions. The XOR is the XNOR of both expressions, and the XNOR is an XOR just negated. Here we have the XOR of C and X. So finally here we have an AND gate, a logic product. So F is going to be the first input of the NAND multiplied by the other input. So this is F. So we have finished A section, where we have to do the same for the G. That is quite easy. So what happened with B? Here we have to build a 2-level logic diagram. So this is saying that we have to calculate a sum of products or a product of sums, just to have or and or 2 levels circuit. So we have to algebraically manipulate the function to obtain a sum of products or a product of sums. So here we have the function that we have just obtained, and we are going to remember the operation of the XOR gate and the XNOR gate are these ones, because we need the function of this operation just in a normalized way, as a sum of products as a product of sums. For the XOR, we have the minterms, these 2 minterms. So according to Shannon, the XOR operation is this minterm with A negated plus B, A negated multiplied by B, A multiplied by B negated. These 2 ones, just applying Shannon. And for the XNOR, we have these 2 minterms that are both inputs negated plus both inputs not negated. So every time we see these operations in a circuit or in a logic expression, we can substitute the symbol by the function, by one function of the other if the symbol is negated. So here we have an XNOR operation because of the negation. So we are going to call this, for example, A, and we are going to proceed with this simplification. The XNOR is the first part negated multiplied by the second part negated plus both parts not negated. So we can do the following. First part multiplied by the second part, both not negated, plus the first part negated multiplied by the second part negated. So we can proceed with the function. Here we have XOR, so we can use this expression, that is the first variable negated, the second not negated, the first negated, the first not negated and the second negated. So we do that. We have this and this. So this is this, and this term is this term, just substituting the expression of the XOR. And now here we have two XNOR, so we use this expression. Plus this is the XNOR, remember. Okay, so now we can apply the distributive property to have just a sum of products. And we are going to have the following. As I said before, I recommend you to order the variables in the product terms. So my order is going to be X, Y, C, and T. Sorry. So this is, all of this is A, but in the function we have the term A multiplied by this XOR that we can do like this. So we apply again the distributive property of this XOR with all the term A. And we are going to have a lot of terms. We are going to have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8 multiplied by 2, 16 terms. So you have to be careful because we can forget things. Okay, just check what I'm doing because I'm human and I can make mistakes as well. I'm just mixing the variables. Sorry. This is negated here, here, and here. So we have the 16 turns of applying that. So now we can get rid of a lot of terms just using the complementation axiom. Remember the complementation axiom, that is this one. So if we have in a product term the same variable and the variable negated, this is going to be 0. So pay attention to this. And we are going to use the idempotent law as well to eliminate some of the repeated variables of the product terms. So we are going to identify these terms. For example, here we can get rid of both these variables by the idempotent law. Here we have the x and the x negated, so it's going to be 0. Here we have we can get rid of the x and the c negated because it's repeated. Here we have the x negated and the x not negated and the c not negated and the c negated, so by the complementation law this is 0. Here we have this, so this is going to be 0 as well. Here we have again the x negated and the x, so it's going to be 0. Here we have the C and the C negated is 0. The X and the X negated 0. The X and the X negated 0. By the idempotent law, we can get rid of the X negated and the C here. Here we have the X and the X negated and the C negated and the C, so it's going 0. It's going to be 0. Sorry. Here we have we can get rid of this X negated and this C by the idempotent law. Here we have the X and the X negated, so it's going to be 0. Here we have the C negated and the C, so it's 0. And here we have the X and the X negated is going to be 0. And here we have the C negated and the C, so it's 0. So finally, we have only 4 minterms, I think. This one, this one, this one, and this one. So our function is going to be the following. These 4 minterms that are the 12, the 9, the 6, and the 3. And this is the disjunctive canonical form of the function, because we have the minterms. So if we remember, the exercise asks if this is the minimum implementation. We have a sum of products, but we don't know if it's the minimum representation yet. So we are going to create the Karnaugh map. For example, here. So the minterms are these ones: the 3, the 6, the 9, and the 12. If we look at the map, we see that we cannot group these ones in larger allowed group as 1. So they are prime implicants of the function. In fact, they are essential prime implicants of the function because they are covering distinct cells. So this is going to be the minimal sum because it's the sum of the essential prime implicants and they are covering all the function. So this is the minimum implementation with the minimal sum. We can check with the zeros. If we draw the zeros, we can start with the Karnaugh map. For example, using this color, we are going to look for the implicates. So we can form an implicate. Sorry, here we have another 0. We can form an implicate here. We can form another implicate, for example, here. Another implicate here. And another implicate covering the 4 corners. So we are going to check the minimal products. So this is going to be implicate 1, implicate 2, for example, implicate 3 here in the corners, and implicate 4, these 4 zeros. I think that all of them are essential. Yes, all of them are essential prime implicates. So they are going to cover all the function. So the minimum product is going to be the product of all the implicates, because they are essential prime implicates. So in the case of the minimal sum, we have how many operands? We have 4 operands. It's an OR gate with 4 inputs. And in the case of the minimum product, we have as well 4 implicates. So we have we have the same number of operands for both implementations. We may check the number of gates that they need. With this purpose, we need to write the sum terms associated to every prime implicate. In fact, we have to do it always. So prime implicant 1 is going to be this. Prime implicant 2 is going to be this. Prime implicant 3 is going to be this. And prime implicant 4 is going to be this. So in both cases we are going to need the same number of gates, but what happens with the inverters? In the case of the minimal sum, we have all the variables with the version negated and non-negated. And the same happens with the minimal product. So the number of inverters is going to be the same. So we are going to need exactly the same number of gates in both cases. So we can choose the expression we want. So following with the exercise, we are going to build the 2-level logic diagram. And I'm going to use the minimal sum, for example. So this was our minimal sum, and we are going to build the logic diagram using 2 levels and OR. The output level is going to be an OR gate, with 1, 2, 3, 4 inputs. So this is the function, and the inputs are going to be 4 AND gates, 1, 2, 3, 4, with 4 inputs. So for example, and now we have to build the products. So x, y, c, and t. In the first gate we have x, y, c negated, and t negated. In the second AND gate we need x. I draw circles to make clear that this is a connection. X, E negated, C negated, and T. In the third NAND we need X negated, Y, C, and T negated. And in the last one we need X negated, Y negated, C not negated, and T not negated. So we have a two-level and/or implementation of F as the exercise asks. But we haven't finished the exercise. The C section tells to construct the minimal logic diagram using two input NAND gates. So firstly, I'm going to implement the circuit using NAND gate without limitation in the inputs, and later I'm going to explain you how to use NAND gate with a fewer number of inputs to implement a larger NAND gate. It's quite simple. So here we have the function, and we have the minimal sum. So in order to have the expression as a NAND operations, I told you to negate the function twice and break the first negation using the De Morgan's law. So we are going to have the following. And in this way we already have the function as a NAND operation expression. So we can start using, we can start drawing the NAND diagram. You may check, as we saw in class, what is the expression of the minimal product using NAND gates with the the more complex method that I explained to you. But if you are short in time, don't try it, okay? Just use the minimal sum. We are going to use the minimal sum here. So we need in the output a NAND gate with 4 inputs. So we have the NAND gate with 4 inputs. And we are going to have 4 NAND gates to implement each operand. So we have the variables and their negations. The variable and the negation using NAND gate. So the first is x, y, x, y, c negated, t negated. The second is x, y negated, c negated, and t not negated. The third none is x negated, y, c, and t negated. And the last one is x negated, y negated, c not negated, and t not negated. So this is the circuit using NAND gate without limitation in the inputs. But we have to use 2 input NAND gates. How can we build a 4 input NAND gate using 2 input NAND gate? We are going to see an example. If we have this is a 4 input NAND gate, and the output is the NAND operation. So we are going to use the following. We are going to connect the input to this level. We are going to invert this output, and we are going to connect the inverted output to the last NAND gate. Here we have this. If we invert this, we have this and this, applying the De Morgan's law. Double negation is just the variable without negation. And here, finally, we have the same result. So we have to use more NAND gate in this case, but we can use NAND gates with fewer inputs. Now I think that we have finished the whole exercise. This is a quite complex exercise. I think it is the exercise with the more complex logic connection. So if you know how to do this, I think that you can make whatever exercise that I can choose for the exam. So we have finished this exercise.